Hey everybody, we're going to keep talking about populations today, but we're going to look more specifically at how we talk about population growth and things that can affect population size. So we have some equations that help us understand population growth. So here we have an equation with the change in n, or population size, over the change in time equals the birth rate minus the death rate. So we're looking at how much a population is growing due to births versus how much it could be decreasing due to deaths, and that would give us our population size. We can also, though, look at the rate of increase. And so here we have R, which equals the difference between the birth rate and death rate. So the number of individuals that are entering the population due to the fact that, births are higher than deaths, or how much smaller the population is getting if it is negative because we have more individuals dying than are being born. So this gives us the equation: the change in population size over the change in time equals the rate of increase times the number of individuals in the population. So now this term is actually the first differential of population size with respect to time. So I promise we're not going to talk a ton about calculus, but that equation essentially becomes the differential of population size over time when you look at the intrinsic rate of increase, so that R max times the population size. So again, this term is the first differential population with respect to time. So I know this is a lot, but we're going to talk about it pretty quickly. So less formally, you can interpret this term as the population growth rate. So how does the population size change if you make a small change forward in time? For an exponential growth function, the key point is that the growth rate is obviously not constant, and that it depends on what your population size is at the moment. And so the bigger the population is already, the faster it will grow. All right, so for exponential growth, the bigger the population size is already, the faster it is going to grow. All right, so with exponential growth, this is characteristic of those R species that we talked about before, and it tends to produce a J-shaped growth curve, and this is only going to hold for ideal conditions and unlimited resources. So exponential growth is not something that you tend to see all the time because it needs ideal conditions and lots of resources in order for individuals to reproduce really quickly for you to see exponential growth. And so this is what that J-shaped growth curve for exponential growth would look like. But what's more common is for us to see logistic growth. And here we have a few new characters, that being K, which is the carrying capacity. So the result here is that you tend to see an S-shaped growth curve. This is characteristic of those K species we talked about this last time, and this is much more common anytime resources are limited. So anytime you've got competition for resources, you tend to see logistic growth. Okay, and so the logistic growth curve is going to be the red curve here. And again, we see this carrying capacity coming in here. So the carrying capacity, or K, is 1,500 individuals. So you've got 1,500 individuals minus N, which is the population size, divided by that carrying capacity again. And I know I kind of skipped over it really quickly, but that is where we get that from. All right, so K is not a constant value, the carrying capacity is not always going to stay the same. It can change, and populations don't often sit right at the carrying capacity. They will kind of fluctuate above and below the carrying capacity as the environment changes with time. And this is just some examples of that. So populations will often overshoot carrying capacity, and then they will drop back down to carrying capacity or even below carrying capacity. So again, the carrying capacity is not going to be like this steady state population. Instead, you'll see populations kind of fluctuate above and below the carrying capacity. So again, AP exam doesn't really ask you to work these equations very often, but you should be able to talk about exponential growth versus logistic growth in populations. So now, how do we regulate population size? We've got two different categories that we're going to talk about. We've got density dependent factors and then density independent factors that limit population size. So density dependent factors they are related to the population size. So as the population increases, mortality tends to increase as well. And this is because you have competition for resources. So you've got competitions for food and water, for mates, for nesting space. Disease is more likely to spread when density is high. And so the what happens then is as density increases, you tend to see more of these density dependent limiting factors. With density independent limiting factors, here the effect is not related to population size. So the mortality is not related to population size. So density independent factors tend to be things that could be related to weather or climate or natural disasters or disturbances, things that are going to happen to an environment regardless of how many individuals live there. So population cycles. So population tends to change cyclically over time. This is often seen in predator and prey cycles. The really classic example is the snowshoe hare and the lynx. And so you can see here that population sizes for both are fluctuating. So the snowshoe hare is in black and the lynx is in red. And so the snowshoe hare would be the prey and the lynx is the predator. And so as the prey species increases in individuals, you can see then there's a lag, but then the predator is going to increase in the number of individuals. Well, after the number of predators increases, you can see that the prey decreases. Because the amount of prey decreases, then the number of predators will decrease because they don't have enough food. Well, once that number is lower, the prey species is not getting eaten as much, and so you will see a spike in their population. Well, now because there's more food available, now the number of prey individuals will increase as well. So you can see that these fluctuate up and down, and the lynx tends to lag behind the snowshoe hare. If there's not a lot of food, then their numbers will decrease. If there is a lot of food, then after the snowshoe hare population increases, then the lynx population will increase as well. So again, these cycles are caused by density-dependent factors, chemical cycles, and a saturation strategy that can confuse predators. So we can use things like age structure diagrams to look at populations. These diagrams show the percent of a population in different age categories. It's a method to get data similar to the life table, but at one point in time. And so these are three different examples of age structure diagrams. And so here we have Kenya, what we're looking at here, and what this shows us is that the vast majority of individuals, both male and female, are much younger. And so if we saw an age structure diagram that looked like this, that looks like a pyramid with a very wide base, we would expect to see very rapid growth because all of these individuals down here are still at or below reproductive age, and so all of these individuals can still reproduce or are still reproducing, and so we would expect to see this population grow pretty rapidly. Here we're looking at an age structure diagram for the US. Now this is going to be much slower growth, and so we still have a decent chunk of individuals at or below the reproductive age, so they can still have babies and cause the population to grow. Here we have slow growth or, zero growth or a decrease in population size. The example here is in Italy. And the way that we can tell that this is going to actually be zero growth or a decrease is because the base of the pyramid is actually much smaller than the widest part, which is up higher, and these individuals are kind of done reproducing or nearing the end of the reproductive age. So again, if you see like a classic pyramid shape, you would expect rapid population growth. If it's pretty stable, you would expect slow population growth. And if it's almost inverted, then you would tend to see either zero growth or a population decrease because now most of the population is a little bit older. Something else to kind of keep in mind when you look at the US and Italy, notice that when you get up to 80 plus years, you start to see or even like 75 plus years, you start to see an increase in or not an increase in, but more females than males when you compare the two at the same ages. So think about that and maybe why that is. So these are really important diagrams because they can be used to predict future population growth trends, especially for long-lived species. These are really helpful too when we look at human populations and how they're changing over time, and they can be used for planning purposes. So exponential growth, again, is going to produce age structures that are a triangle or pyramid shape, like the Kenya one. Logistic growth produces age structures that have even sizes between most age categories, so the example there was the US. And then the declining populations produce age structures with a narrow base and wider middles, like in Italy. All right, so your summary for this chapter, you guys should be able to talk about population density and dispersion patterns. You should understand life tables and survivorship curves. You guys should be able to compare and contrast R and K species and the strategies that they use. You guys should know exponential and logistic growth curves and equations. More importantly, the curves and what they mean. But if given the equation, like you should be able to talk about the equations and what they mean. And then also density, I should say density dependent and density independent growth factors. So you should be able to talk about both of those. All right, and then your lecture question for today is which type of limiting factors are capable of quickly wiping out almost an entire population in a single generation? So we talked about, again, the density dependent or density independent. So I'd like you guys to think on that question and shoot me a message through the class website. Thanks, guys.